Hello and welcome to the second video of the M2 chapter, Impulses and Collisions. Another starter on the screen here to review the M1 work, as with the previous video. Two particles A and B are travelling in the same direction on a smooth horizontal surface with speeds 4 and 3 respectively, such that they collide. That means A must be catching up to B, otherwise they would never collide. 4 here, 3 here. Particle A has mass 2 times that of particle B. Okay, we don't know what that is, but let's call particle B m, so A is 2m. After the collision, particle B continues in the same direction with an increased speed of 5. Determine the speed and direction of particle A. So I will take this as my positive direction. So I'll make v in this direction initially, and then if it's negative, I know it's the other way. So all I need to do is apply conservation of linear momentum. We have 2m times 4 for particle A here, plus m times 3 must equal, after the collision, 2m times v plus m times 5. Collecting like terms gives us 6m, 2mv. Cancelling those gives us v must be 3 meters per second. Positive, therefore the direction has not changed. It is still in the direction as A before the collision. In this video, we're going to look at Newton's law of restitution. Jumping straight into that, Newton's law of restitution is a ratio, and it's a ratio between the speed of separation of two particles, how fast they move apart, and the speed of approach of those same two particles, i.e. how fast they came together towards the impact. So it's this, speed of separation divided by speed of approach. How fast they move apart after the collision compared with how fast they come together before the collision. And this is given the slightly unfortunate letter e, because we're used to e being a fixed number in our exponential work, but here in this video e is an unknown that represents the coefficient of restitution. So if you imagine 3 different balls, you've got one made of metal, one made of wood, one made of Play-Doh. If you threw them all at a concrete wall, they would rebound in very different ways. The metal one would come back very quickly, the wooden one would come back fairly quickly, and the Play-Doh one might not come back at all, it might just splat against the wall. That's an example of what this next sentence means. The coefficient of restitution is specific to the material of the particles involved, and it's a measure of the elasticity of the collision. If it's very elastic, it means the ball will rebound with something close to the speed it had going in. If it's not very elastic, we might say it's inelastic, then the particle will rebound with a much slower speed than when it went in. And I'll do a very quick example to show you how this ratio works in practice. Determine the coefficient of restitution for the following two particles. So the ratio is speed of separation over speed of approach. So how fast do they separate? That's after the impact. So you can see here we've got 5 meters a second and 3 meters a second. The difference there is 2 meters per second. The speed of approach, 7 meters a second, 3 meters a second. So the speed of approach here, 7 minus 3, is 4 meters per second. So our ratio 2 over 4 is a half for E. And you can see that this has nothing to do with the mass, it has nothing to do with momentum. Linear momentum is still conserved. It's just relating the difference of the speeds before and the difference of the speeds after the impact. Now when I say the difference there, I've got to be a little bit careful. You can see I've used the difference here and here. But if they were travelling towards one another like this, 7 and 3, then this of course you'd have to remember would be negative 3 in a directional sense. So when you did this, you'd be adding them together. And on the other side, if they separated out like this, 3 and 5, again this 3 would be a negative 3. And if we said minus 3 minus 5, if we wanted to do it that way, we would have to change that into a positive number because it's a speed we're talking about in the ratio, not a velocity. So in the situation in red, we would have a very different e value. It would be 8/10 or 4/5. So I hope that shows that the ratio itself is fairly straightforward. You've got speed of separation, speed of approach, and they give you a value for e, specific to those two particles. There are some limits on what e can be. The maximum value, the largest value e can take, is 1, and this represents a perfectly elastic collision. We'll talk a bit more about what that means and why that's important in the next video when we talk about kinetic energy, but for now I hope you can see that if the speed of separation and the speed of approach are the same value, then this will be a 1, and I'm sure you can appreciate that unless there is something else going on in the situation, the speed of separation is never going to be bigger than the speed of approach. So that's an upper limit for e. There is also a lower limit. Obviously this ratio you're never going to get anything less than 0 because you can't have a negative speed. And if it is 0, this represents a perfectly inelastic collision where the two particles have coalesced and combined into one particle. And if you think about it for a moment, the speed of separation, this number on the top, if that's 0, that means that they are not separating. And that, of course, is what coalesced means. They've combined and they don't separate anymore. So it's important to remember that E will always be between 0 and 1. 2 more examples with this ratio, and then we'll look at how this fits in with the things we already know. Determine the coefficient of restitution for the following two particles. This is similar to the previous one, but here we've got the two approaching. So here we've got 8, with this as a positive direction for the velocity. Here we've got -4. So the difference in the velocities here gives us a 12. Now I say, okay, I need a speed, not a velocity, so the magnitude of that, which of course is still just 12. So the speed of their approach is 12. Over here, velocity -4, velocity 1, -4 -1 gives us a difference of -5, but we need a speed in the ratio, not a velocity, so the magnitude of this becomes 5. The ratio is the speed of separation divided by the speed of approach. So here, our coefficient of restitution is 5/12. I should mention at this point that you won't see this in the textbook. What the book does is just say you should be able to realize this with a bit of logic. If they are going towards one another, then you should be adding the numbers. If they're going away from each other, you should also be adding the numbers because you want the relative speed between them. You only want the difference if they're going in the same direction. So while I hope it's helpful to have seen this, as we go into the following examples, I won't use that magnitude symbol anymore. I will just make a judgment call as to whether we should be adding these numbers or finding the difference between them. Next example. Two particles, A and B, are traveling in the same direction on a smooth surface with speeds 4 and 3 respectively. So A here, B here, 4 and 3 going in the same direction. They collide directly and immediately after the collision continues to travel in the same direction. Okay, so they're still going in this way with speeds 2 and v respectively. Given that the coefficient of restitution between A and B is 1/3, find v. Looking first at the speed of approach, that's quite easy. They're in the same direction, 4 minus 3. There's a relative speed there of 1. The speed of separation is a little bit more tricky because we've got 2 and an unknown. So should it be v minus 2 or 2 minus v? In this case, the context of the question gives us the answer. If particle A has caught up to particle B and they've collided, then particle A after the collision is not going to catch up to particle B again. It doesn't keep bouncing off particle B as they go along. That doesn't make any sense, unless there's some other force acting. So after the collision, if they are going to separate, B must have a speed greater than A. So whatever V is, it should be bigger than 2, so I'm going to write V minus 2. Our ratio then, E, speed of separation over speed of approach, in this case must equal 1/3, so V minus 2 is equal to 1/3, V is equal to 2 2/3 or 7/3 meters per second. Now let's see how it ties in with what we've done. If you use the ratio together with the conservation of linear momentum, we can solve problems involving two unknowns, because this gives us obviously two equations to work with. The v1, the v2, the u1, the u2 will be in here as well, and you can solve them as simultaneous equations. One key thing to remember as you're doing these problems, though, is the direction of travel. That's very important. Not only is it important with these ones when you're talking about velocity, to make sure that you've got a negative sign where you need it, but also here, as we saw in the previous examples, if they're approaching each other in the same direction, you find the difference. If they're going in opposite directions and collide, then you add the two speeds together. It's easy to make a mistake on that. So just remember that the direction of travel is very important in these problems. To finish the video, two much more involved examples. First one here. Two particles A and B of masses this and this are traveling in opposite directions towards each other with speeds this and this. Okay, so before the collision, two particles, 0.2, 0.4, this is A, B, traveling in opposite directions towards one another, speeds 5 and 4. So this is before they collide directly, and immediately after the collision, they have velocities v1 and v2. Measured in the direction of motion of A before the collision. So we're measuring them in this direction. That's very clear in this example. Given that the coefficient of restitution between A and B is a half, find v1 and v2. So this is a very standard problem. We've got conservation of linear momentum, which will give us one equation, Newton's law of restitution, which will give us a second equation, and we've got two unknowns then with two equations. We can solve them simultaneously to find both. For shorthand, if you want to make it clear for your examiner, you can use CLM, and your examiner will recognize that as conservation of linear momentum, and Newton's law of restitution, NLR. So for momentum, we've got 5 times 0.2 plus 0.4, and I usually put my minuses on. I didn't do that this time. Minus 4 because it's going in the other direction. Must equal 0.2 times v1 plus 0.4 times v2. On the left, we've got 1 minus 1.6, that's minus 0.6, 0.2 v1, 0.4 v2. I don't like any of those decimals, I'm going to get rid of them all. Minus 3 v1, 2 v2. That's our first equation. Jumping over to Newton's law of restitution, we've got the speed of separation, v2 and v1 here, and as with the previous example, unless there's going to be a second collision, we know that this velocity must be greater than this velocity. That doesn't mean the speed has to be greater than this speed, because the direction of this one might be reversed. It might have a greater speed, but in the opposite direction. But if this velocity was bigger than this one, then they would collide again, and that doesn't make any sense. So I'm going to put v2 minus v1, because I know if I put the velocities in, that will give me a positive answer, and that will represent the speed. Divided by 5 minus minus 4, or just adding the two speeds, 5 plus 4, the speed of approach, has to equal 1/2. So we get the relationship v2 is equal to 9 over 2, take the v1 on the other side, v1. From here, it's just solving simultaneous equations. I'm going to put this one into this equation by substituting out v2 for this expression. So minus 3 is equal to v1 plus 2 lots of 9 over 2 plus v1. That gives me 3v1 plus 9 minus 3. So we get minus 12 on the left. 3v1, so v1 is equal to minus 4. Putting that back into this equation here, v2 is equal to 9 over 2 minus 4. v2 is equal to 1/2. I think the most interesting point there was this. Knowing that v2 had to be bigger than v1 in terms of a velocity meant I could write this expression without worrying about having created a negative speed. Final example is even more involved, so I'm going to do it over a few different screens. Two balls P and Q have masses 3m and 4m respectively. They are moving in opposite directions towards each other along the same straight line on a smooth level floor. Immediately before they collide, we've got 3u for p and a speed of 2u for q. So let's draw this up. We've got p here, mass 3m, q here, mass 4m, p is travelling at speed 3u, q is travelling at speed 2u, velocity minus 2u. Taking this direction to be my positive. Back to the information. The coefficient of restitution between p and q is e. That's particularly awkward that they've just left it as e. Just keep in your mind here that e is an unknown value to find. By modelling the balls as smooth spheres and the floor as a smooth horizontal plane, show that the speed of q after the collision is this. After the collision, the mass has not changed. I will start with them both in this direction, allowing for the possibility that they might be negative velocities. Now I form my two equations. Conservation of linear momentum. We've got 3m times 3u, so 9mu, plus 4m times minus 2u, so minus 8mu, must equal 3m times v1 plus 4m times v2. All of the m's cancel nicely, and we get 1u is equal to 3v1 plus 4v2. There's our first equation. Newton's law of restitution. Same arguments as before. I know that v2 as a velocity must be greater than v1, otherwise there would be a second collision, and we have no reason to think that there will be. v2 minus v1 divided by the speed of approach, this minus this, or just 3u plus the magnitude of this 2u. Either way, we get 5u. And we're told that the coefficient of restitution is simply e, an unknown. This gives us v2 minus v1 is equal to 5eu. And because I want to find the speed of q, I want to isolate v2, which means I want to substitute v1. So v1 is equal to v2 minus 5eu, and I can put that expression in this equation here. So we've got u is equal to 3 times v1, which we now know is v2 minus 5eu, plus 4v2, 3v2 and 4v2, 7v2, minus 15eu, that equals u. Rearranging that, we get 7v2 is equal to 15eu plus u, factorize out the u, 15e plus 1, and of course divide by the 7, and we get our final answer. Part B. Given that the direction of motion of p is unchanged, find the range of possible values of e. So I've put the velocity of q up here. But let's go back to our diagram for a second. We've just been told that the direction of p is unchanged. So it was going this way, it's still going this way. That means q must also be going this way because v2 we know must be bigger than v1. The key problem-solving element of this question then, the direction of motion of p is unchanged, that tells us an inequality. v1 must be bigger than 0 because I've chosen this as my positive direction, and what that's saying is if it's unchanged it's still positive, v is greater than 0. So that sentence is giving me my starting point, v1 greater than 0. Given that, find the range of possible values of e. I'm going to have to go back to the screen again because we've got vq, which is v2. But we did have this expression here, v1 is equal to v2 minus 5eu. So we also know that v1 is equal to v2 minus 5eu. We know v2 up in the corner, u over 7, 15e plus 1 minus 5eu. And as we've noted already, this must be greater than 0. Now I can rearrange this and find the range of e. 5eu on this side, u 15e plus 1 over 7, the u's will cancel out, take the 7 up, gives us 35e, 15e plus 1, that's 20e, So E must be less than 1/20th. But don't leave it there, because E should have two sides for its inequality. We know that E should be less than or equal to 1. Here in this example, we know it's actually less than 1/20. But the other side, we also know it must be greater than or equal to 0. Don't forget to put that bit on. Or if it had been the other way around, if we had found a result for this side, then don't forget to put less than or equal to 1 on this side. Part B finished. Part C. Given that the magnitude of the impulse of P on Q is this, find the value of E. We don't need the previous screen for this, because impulse is taking us back to this equation. Specifically, we're looking at Q, the impulse on Q. We know the final speed of Q was this, and the initial speed of Q was this. Putting those in here, together with this information, I can say that 80 mu over 9, the impulse, must equal the mass. We know the mass of Q is 4m, times the velocity, the final velocity, u over 7, 15e plus 1, minus the mass, 4m again, times the initial velocity, which was 2u. Now, here is a key point. I have made a mistake. If I keep going here, I will get the wrong answer. And this is what I was emphasizing earlier. You must be careful with your direction. I said velocity is 2u. That's not true. The speed was 2u, and given all of the things I've done so far, including how to find this value here, I was using this direction as positive, and the 2u was negative. That's important because we used the directions to get this, so I need to be consistent with those directions. The velocity is negative 2u. Now I should be okay. This gives me 4mu over 7, 15e plus 1 plus 8mu, 80mu over 9. Now we can cancel the m's and the u's from each term, and all we've got left is E, the thing we're trying to solve. Take the 8 on the other side, do all of the calculations, and you will find that E is equal to 1 over 27 as your final answer. That example was quite involved, but I think the easiest place to make a mistake was right here with the directions. So I hope that's enough now for you to have a go at the questions in exercise 5b, and maybe I'll see you in video 3.